Test. Est-ce que vous m'entendez? Ça marche?
Who is actually from Diffusion, from here, from even this floor, I think. Very low. and he's going to tell us about combinatorial geometries and determinantal measures on graphs.
Thank you very much, Rémi, for the introduction, and I'd like to start by thanking all the organizers for putting up this very nice workshop and for giving me the opportunity to speak about my work. So I'm indeed from this lab. I think it's the first time I give a talk so close to my office, so the conference came to my office. It's very, very nice of you. So today I will talk about joint work with Thierry Lévy, who is just here. About discrete determinantal processes. So the outline of my talk will be as follows. First, I'll recall determinantal measures in the discrete case from a classical point of view, but maybe which is not most common, so I thought it would be nice to just recall a little bit how we think about them. And then I'll talk about so-called combinatorial geometries, which are a deterministic thing, sometimes also called matroids, and which is a classical part of mathematics, which is useful to think about the kind of random graphs we want to talk about. And then I look at random such combinatorial geometries, an example of which are random spanning trees. And then I'll talk about our still ongoing project about these geometries in higher rank, and I'll define what that means. So first of all, let me start by recalling what are these discrete determinantal measures, how we think about them. Whoops. Okay, so the setup is the following. We have a Euclidean space, a finite dimensional Euclidean space E, and a certain subspace H of that space. And we fix an orthonormal basis, E1, ED, of that space. So for example, in this drawing, you have E, which is R3, a usual orthonormal basis of it, and H is this two-plane. Now, when you take an orthonormal basis of H, like representing, for example, this little square here in this plane, the so-called Plücker coordinates of a subspace are basically what I represented here on the drawing, which are projected shadows of this little square on the coordinate subspaces. And these are scalar coefficients which represent basically these areas, except they have signs because it depends on some orientation. And in fact, it turns out that when you take an appropriate normalization, the sum of squares of these Est-ce que ça va?
C'est bon.
C'est bon?
Merci.
Okay. Okay. So so this name was coined, I think, by Alexei Borodin around 2000, and of course these are the point processes which were introduced as fermionic point processes by Odile Mackie in the 70s in her foundational work. Although I guess she was more working in the continuous, and this is the purely discrete case, finite case. Now let me state another geometrical fact which is known and is basically due to lines, but maybe was not exactly phrased in this way, which I call the mean projection theorem. So remember now I have my setup, which is a random point a random subset X of a certain set, and these EIs are the orthonormal basis of E. Now I can look at the coordinate subspace spanned by this X, and this defines just a random coordinate subspace. So it turns out that E factors, is a decomposition not orthogonal of this random coordinate subspace Q plus the H orthogonal. So like Q and H orthogonal are complements, linear complements. And if you look at the projection on Q parallel to this space, I should have maybe prolonged them, H orthogonal, on average, you get back, if you take the average over the point process, you get back the orthogonal projection on H. So this is what I call the mean projection theorem. Okay. So now let me move on gradually to these combinatorial geometries. So if we're interested in the support of this measure, right? So in the discrete case, not all n subsets will appear. There are strong conditions. So the n subsets I for which the probability that x is equal to I is strictly positive. If you think about what it means in terms of the definition I gave, they are precisely those subset I's for which when you project the vectors EI on the subspace H, this family is linearly independent, and thus it forms a basis of H. In particular, if this family is linearly independent, every subfamily, if you take J included in I, which satisfies this, is linearly independent. And so now you see that it defines a new notion of linear independence on the family of vectors. You started with some vectors. It's very simple, but you started with some vectors. You project them on a subspace H. And now you say, in the initial family, I'm going to say that a certain family is linearly dependent if it's linearly dependent in its image in H. So there's nothing very complicated in that, but it turns out that it's interesting to think about this as a new notion of linear independence on the subset S. And this is an example of combinatorial geometry as I'll define in the next section. And in particular, in our case, this combinatorial geometry is random, so it's measured. And indeed, the incidence measure assigns a weight to each independent set. And when you restrict C'est bon?
Oui.
Alors, vous pouvez m'aider à remettre juste, c'était...
Il ne faut pas toucher le bouton. Si on peut mettre une poche.
Ah, poche, ouais.
Ouais. Surtout, il ne faut pas toucher.
Le bouton qui est au-dessus?
Voilà. Ah, parfait.
Bon,
Ça, c'est bon.
on va essayer. Okay. So let me move on to these combinatorial geometries on graphs. So now for this section, there's no probability. It's combinatorics. So let me just there's one definition, and then we'll see examples. So a matrid or combinatorial geometry. So I prefer this term because I find it more inspiring, and actually it was proposed by Giancarlo Rota, but it never really took. And the name matrid was introduced by Whitney in his foundational work on the subject, which I learned recently was also independently carried out by Nakazawa in Japan. So if you're given a finite set S, a notion of combinatorial geometry on this finite set is a non-empty collection I of subsets, which you call the independent subsets of S. So they will define for you what are independent. And all subsets which are not independent are called dependent. So and these define for you what are dependent. And so, of course, if you want some properties to be satisfied, you cannot take any I, so they have to satisfy two axioms. The first is a hereditary property, so if I is included in capital I, and J is a subset of I, then J must also belong to I. And the second one is more subtle and is reminiscent of how is it called again in linear algebra, basis completion lemma or something, basis something like this. If I and J are independent sets and J is smaller in cardinality than I, then there exists an element in the bigger one which you can add to the smaller one such that J union I is in I. And okay, so that's the definition. Now, independent sets which are not included in any other ones, so the maximal ones, are called bases. And dependent sets, which are all the sets which are not independent, which are minimal, are called circuits. So the name will, the origin of this name appears clearly from the origin of the theory. So the two founding examples which motivated Whitney are the following. The first is from linear algebra. So you take S, as we did before, a family of vectors in a vector space. And you take I to be all the linear subsets of this family which are linearly independent. If you take a maximal such thing, it's a basis, hence the name here basis. The other context is graph theory. You take S to be the set of edges of a finite graph, and you take I to be all the subsets which do not contain a cycle. Well, what are the minimal subsets of edges which do contain a cycle? They are precisely the simple cycles, hence the name circuits for these minimal dependent sets. And so in this talk, all the matrices, all the combinatorial geometries I will talk about, even this one, the second one, they can be represented as an example of linear algebra in that way, and it's called, to represent linearly a matrid. But one interest of this theory, but it's not the only one, is that there are also examples of matrices which have no linear realization. So that's a huge theory. There are huge books about all these things. But even though I'm going to talk only about examples such as the second one, which actually can be seen as examples of linear algebra, it really does help to think about this object, to think about this framework. Okay, so first example is it corresponds to the second line here, and this is called the circular matrix. So you take S to be the edges of a finite connected graph, I to be the collection of all spanning forests. And this defines a matroid, which is called a circular matroid. The bases are the spanning trees. So here I represented one. So the underlying graph G is just a square grid, and here you have a spanning tree. And the circuits are the simple cycles. The name circular comes from the fact that the circuits are just cycles. And just a comment, so there's also an interest when you look at these geometries to try to know if you can enumerate the bases. And in that case, this is just the famous matrix 3 theorem by Kirchhoff, which says that you can compute this number of spanning trees by computing a determinant. Now, given a matroid, there are many things you can do about them, but there are also, for example, operations you can do to construct new ones. So two simple operations are the following. You can take the union of two matrices on the same set by just taking independent sets to be unions of independent sets of both. And another one, which also, if you are familiar with discrete determinant of point processes you have encountered, which is taking the dual, which is you take, you can define also the matroid by their set of bases, because all the independent sets are just the subsets, all the subsets of these bases. And you can define a new set of bases by taking the complements of the bases of a first matroid inside S. So now what I'm going to show is that from the circular matroid, by doing very simple operations like these, one can generate new matrices on graphs. And then in the next part, I will give explicit examples of determinant of probability measures, which are not just uniform measure on these guys. Okay, so here a first family of two examples. So the drawing, which one did I start with? Okay, so I'll explain this notation later, but then let me call it the first matroid MK0. So it corresponds to this picture. So I claim that if I fix an integer k, and I look at the spanning forests which have k, well here, just for some reason, I'll index that by k plus 1 connected components. I claim that if I fix this k and I look at these are the bases of a matrix. And the circuits in that case, they are the simple cycles, as in the tree case, but also spanning forests with k connected component. Because if you have k connected components, it's already, it means they are dependent in some sense. Because bases should have k plus 1 connected components. A sort of a dual, at least in the planar graph case, is connected subgraphs with a fixed number of cycles. So here what we see is random, well, forget the random for now, but it is random. A subgraph of a square grid graph, which is connected. And in black, I have represented basically the two core of this graph, and you see that it has 1, 2, 3, 4 cycles. So I claim that if you fix some L and you look at all the connected subgraphs with fixed L cycles, these are the bases of a matroid, and the circuits in that case are the middle subgraph with L plus 1 cycles. And here again, there's an interesting fact about counting the number of bases of each of these. So I think this is an not well enough known result by Liu and Chao, and which was a little bit simplified by Myhrvold, which gives an explicit formula, which is a linear combination of determinants, but which you can compute in polynomial time, to compute the number of forests with k component. So yes, and I insist on the fact that k is fixed here. It's not counting all the forests, because this is actually probably not known if you can do it, or probably it's not likely to be polynomial. Now there's a question which I don't know the answer to, which is, so in the graph case, let me just give this example. If you have a k component forest, and you draw basically what we call the planar dual of this graph. So you look at the dual graph, which is what you draw in the complement of the faces of this graph, and you take edges which are not crossing any of these edges. you see that if you take the planar dual of a k plus 1 forest with k plus 1 connected component, it will give you a connected subgraph with k cycles. Basically, because in each of these cycles you will have a different tree. So in the planar case, because you can compute this, you can compute this number. But can you do it in the case G is non-planar? I don't know. Or find a formula, and this is something I would like to know. Maybe it is known, but I don't know. Yes, so now let me quickly explain that you can define more generally other classes of subgraphs. Let me first show a picture maybe. So, subgraphs which have several connected components, several cycles, which are a bit of a mix of all the two, but it's not, it's not just any graph. There are some conditions, and this is what I have written, some topological conditions. This is what I have written on this slide. So let me briefly explain it. So here I denote, given any graph or subgraph, I denote by B0 its number of connected components, and I denote by B1 its number of independent cycles, which you can compute by this formula. Now, I'm looking here in a coordinate space which is parameterized by B0 and B1, and I'm saying that, so here, okay, if I take a subgraph which has one connected component and 0 cycle, this is a spanning tree. If I take a graph which is B01, so it's connected, but it has several cycles, this is an example of this connected subgraph with fixed number of cycles. This is in blue. In red, this is a subgraph with 0 cycles, but with a fixed number of connected components. So any of these green points corresponds to forest with fixed number of connected components. Now what I claim, so it's written by these inequalities, but I'll show it on the picture. If you take an integer KL, which just parameterizes a point like this purple point, and now you take this line, so it's defined by these equalities. I claim that this, if you take all the subgraphs that satisfy, for which the B0, B1 satisfies the inequality such that they lie in this subset, they form the basis of matrix, which I call MKL, and I call BKL the set of bases. And an example, so all these blue and red points corresponds to what I have presented here. And I claim that, for example, this point corresponds to this drawing. So it's all the subgraphs which have, so in this subgraph, for example, you have 6 connected components. You have 3 cycles here in bold. And you can compute its Euler characteristic, which happens to be 3. And there are other subgraphs which satisfy the same conditions, so which lie in here. And I'm saying they form the basis of a matrix. Yes, just to end this part, which is non-random, let me say that this is just to say that there are other families of interest in the combinatorial geometries on graphs, but these are absolutely not the only one. I just computed in a simple way some others. But there's an important other example, which is called the bicircular matrix. We have seen the circular matrix, now we have the bicircular. And what is this one? You take, again, S to be the set of edges of your finite connected graph, and now you define the independent subsets to be the collection of subgraphs which have connected components which have at most 1 cycle. And so the basis of these are the subgraph, each of whose connected components has exactly 1 cycle, and they are represented here. And this is what I call forest of unicycles, spanning forest of unicycles. And the circuits, if you think about it, they are the minimal connected subgraphs with 2 cycles. So I have represented often in combinatorics, people talk about them in this way. So you can imagine having these, theta graphs, or like 2 cycles touching at one vertex, or 2 cycles joined by a path. But basically, from the point of view of their number of cycles, they're all in the same family. And now again, a remark about counting. It has been showed by Jimenez and Noy that counting this number of bases is hard. So you won't find a determinantal formula. But however, recently, Guo and Jerome have shown that you can find an approximate counting method to count them. So this is matrix which somehow behaves very differently from the circular case. And by the way, just the name, it's called bicircular because the circuits are these bicycles, I mean these two cycles graphs. Okay, so now the goal of this next section is to give you examples of determinant or probability measures, explicit ones on some of these geometries we have seen. So for this, I will just need a little piece of notation on a graph. So introduce vector spaces of forms on the graph. So a zero form is just a function on vertices. A one form is a function on edges, which is antisymmetric under edge orientation reversal, and will denote by omega 0 and omega 1 the vector spaces of zero forms and of one forms respectively. And given that, you have this notion of discrete derivative, which takes a function on vertices and takes the difference, df on an edge, just a function at the endpoint minus the function at the starting point. And you have a sort of discrete divergence, which is the adjoint of D for appropriate scalar products, which is defined like a D star of one form on evaluated at the vertex is the sum over edges arriving at this vertex of the value of the form on these edges. And just to finish these notations, we will be interested in the image of D and also in the kernel of D star. And we just have, because D and D star are defining that way, we have an orthogonal decomposition of the space of one forms as the direct orthogonal direction of the image of D and the kernel of D star. So the first example is about spanning trees, which we talked about, and the uniform spanning tree measure, which is a very classical example of determinantal measure, and this was proven by Burton and Pimentel in '93. And they have shown that the uniform measure on spanning trees of a graph, so here the graph is the square grid, you have a spanning tree, you take one uniformly at random. It is determinantal on E. So now I'm going to use the notation from the very start where I had a Euclidean space and a subspace, and now my subspace is just omega 1, the space of one forms. My subspace is going to be the image of this map D. And I didn't precise what is the orthonormal basis I'm talking about for omega 1, but omega 1 are one forms, and I'm just going to take a sort of canonical basis, which is that for each edge, I look at the one forms which have a support just on that edge. So basically, if you fix an orientation of each edge, it gives you an orthonormal basis of the space of one forms. Any one form can be written as a linear decomposition of just its values on each edges. So it will be implicit in all what follows that the orthonormal basis of one forms I'm thinking about is determined basically by edges, and there's a choice of orientation, which doesn't matter. But the important fact I want to stress is that we know explicitly what is the subspace, it's this image of D. And we also know what is this determinantal measure. It's assigning a uniform weight to all spanning trees. And yes, this is basically equivalent in some sense to the sentence which is written above, which is that the circular matrix is linearly representable. And in fact, a subset of edges is independent if and only if, when you project this set of edges on the space image of D, these are linearly independent. This is in some sense not a very long fact to prove, but it's a little bit subtle, but it's equivalent. Okay, so now let me give some, so probably many people had seen the previous examples, let me show some other ones. So let me now look at these connected subgraphs with fixed number of cycles. And now I'm not going to look at a uniform measure or something like this, because this turned out to be a sort of miracle. But I will build a measure using some additional data. So I fixed theta 1, theta k to be some one forms, which I take in this kernel of D star. now, given a subgraph like this, I take a basis of its cycles. So for example, I would take this cycle, this cycle, this cycle, and this cycle. And for each cycle, I can compute the integration of the one form along that cycle, which is just taking the sum of the one forms along that cycle. And using these k forms and these k cycles, I can build a k by k matrix, theta e of gamma j. It's a k by k matrix. And I compute its determinant, I take the square. I'm saying this is the weight I want to assign to such a subgraph. Using this, I can define a probability measure just by normalizing it. And what we have shown with Thierry Lévy is that this probability measure is determinantal, and the subspace is very simple to describe. It's just the subspace H is just the image of D as we had seen before, plus the span of these k forms. So plus a k-dimensional subspace, which is just this thing. So let me give another example corresponding to the other family I talked about, which is this spanning forest with fixed number of connected components. So again, I need an additional piece of data to define a measure. So I will take phi 1, phi k to be one forms in the image of D, which are linearly independent. And now for each forest like that, you can see, there are different connected components, and each connected component defined a cut set, which are basically all the edges that would connect this connected component to the rest in the underlying graph. In the planar case, if I were to draw these cuts, they will actually correspond to cycles of the dual graph, as I said before. Anyway, so it defined, you can think about this as even as a free abelian group, and you take a basis of this thing. But intuitively, think of this as just taking for each connected component -1, because there's a linear dependence, the cut determined by that. So it's a collection of edges corresponding to the outgoing edges of that connected component. So you can compute, given a cut, the integration of that one form along this cut, which is basically just like the flow going out along that cut. Again, it defines for you a k by k matrix. I take the determinant, I take the square, I normalize, it gives me a probability measure on these spanning forests, and this is again a determinant of probability measure. And now the subspace is a subspace of the image of D. It's a smaller space, which is obtained by taking image of D intersected with the orthogonal of the span of these phi 1, phi k. And let me just make a remark, is that if you look at the partition function of all these measures, which you would just write as a sum of all the configuration of their weight, a weight would be this thing, times the product over the points inside the process of some variable xi, this is a polynomial. It turns out that in the case k equals 1, this is what is called the second semantic polynomial, which comes from physics originally, but has also many current applications in algebraic combinatorics. And also just because of these determinantal properties, all the partition functions of the measures, in fact all determinantal measures, but these are determinantal measures with explicit weights, they are all stable, which is a very interesting property of polynomials due to a result of Bosser, Branden, Linget. So I think I have roughly 10 minutes, so that's good. I'm arriving to my last part. So now I would like to explain, which was in some sense our motivation, and it still has our ongoing work, how to use this point of view to define random combinatorial geometries arising in higher rank. And what do I mean by higher rank? I have considered forms on graphs which were just functions. Now I would like to fix an integer n and look at vector valued one forms. I would think about it in some sense, it's like spins, but taking vector values over the graph. and what we will call a unitary connection H, which is basically the data of some matrices along edges. So let me just explain by these drawings, first of all, the motivation and then the definition. The motivation, in some sense, comes from geometry. So if you think about your graph as being embedded in a manifold, n-dimensional manifold, and you can think about over each point you have a vector space which could be, for example, the tangent space. And if an arrow is embedded in the manifold, it defines a path for you between 2 points. And if you're in a manifold like this, there's a notion of parallel transport between the tangent space at one vertex and the tangent space at the other one. And I can define H to be the parallel transport along that edge. It's an isomorphism between this vector space fx over x and the vector space fy over y. And here I think about these vector spaces as being all isomorphic to c to the n if I'm in dimension n on a complex manifold, say. So, okay, that was the sort of geometrical motivation why we would be interested in this. But then very concretely, it means imagine over your graph, you just think that you have a copy of c to the n. And now you define with appropriate indices h, e, x corresponds to going from x to the middle of the edge e, etc. Just unitary matrices, n by n unitary matrices which you think about as just connecting your vertices and your midpoints over the edges. And now you can define a twisted notion of our discrete derivative from before, which is now you take a function which is vector valued in c to the n over vertices. How can you define what is its discrete derivative as a one form over edges? Well, you want to take into account these parallel transports, so you take the vector here, you multiply it by the matrix H along that segment. It defines for you a new vector. You take the vector here, you transport it by your matrix here, it gives you a new vector, and then inside that subspace you take the difference. So I don't write the formula, but this is the definition. Let us first start in the case we come back to n equals 1. Actually, if you introduce these h's, which are now just unit complex numbers if you want, already it gives rise to new distributions. So recall what is a forest of unicycle. It's a thing like this, which is a spanning subgraph, each of whose connected component has exactly one cycle. And now define a probability measure which is proportional to the following weight. You take the product of all cycles, and for each cycle you compute the product of the h's, which is a complex number and which we call the holonomy, along that cycle. Take 1 minus that number, take the square, take the product. That's the weight, and define a probability measure. So Kenyon has showed that this probability measure is determinantal, and what is the subspace associated? It's just the image of this covariant discrete derivative. So it's really the analog of the Burton-Pimentel theorem, except that now, because of this presence of this H, you don't have spanning trees, you don't have the uniform measure, but you have this thing. And actually, just to connect to what I said before, now if you take H which tends to 1 in the sense that you take these parallel transport to be very, very, very close to 1, you take them to be e to the I t theta, and you let t tend to 0, then you will see that your measure concentrates on the unicycles with only one connected component, and the weight is exactly the case k equals 1 of the theorem here, where you have one cycles and then the weight is just theta of gamma squared. Okay. Now what's happened when n equals 2? So when n equals 2, one method to define a determinant process is to say, okay, we know what our space, Euclidean space E is. It's just a space of one forms. We know what a tentative subspace H would be, which is the image of this covariant derivative. And now we need an orthonormal basis to define a determinant process. So we just take, as before, for each edge, we look at the one form supported on edge, but that's a vector space of dimension 2 because there's a dimension 2 space over each edge. So I just pick an orthonormal basis over each edge. And now what I have shown, and given this, I can define a determinantal process. And how did I represent it? You should think about these two drawings as being, if you want, one on top of each other. The subgraph is, the underlying graph is the square grid. And these are two layers corresponding to our sample, which you can then view as two subgraphs, but they are coupled. And I will call these two subgraphs x1, x2. The problem, and here I decided to, so you can define this for any n, and there are results for any n, but already at n equals 2 it becomes complicated, so I focus on this. The problem is that here we see something, and okay, I know from the abstract theory that this is a combinatorial geometry. I know that the determinant measure is this, but can I, is the measure uniform? What is the correlation between these things? It turns out it's already very complicated. So let me give some baby examples where we can say something. The first example is when we just take H to be the identity. Well, you don't get back just to the spanning tree model. You get something a little bit different depending on how you have chosen things. So if I want to look at the graph x1, what I have done is above each edge, I have picked a unit vector, which corresponds to, is the first, if you want, of the two unit vectors I have picked over each fiber. And I'm now just going to look at the law of this graph x1. And what I claim is that in that particular case, when H is the identity, the kernel can be just written. It's just a Hadamard product of the kernel for the uniform spanning tree, which I denoted T because it's sometimes called transfer impedance for electrical network reasons, multiplied by the coefficients of this Gram matrix of these vectors. And so this kernel, just by the theory, usual theory of determinantal process, it's indeed a kernel which is self-adjoint and between 0 and 1, and its law is the law of the first component. And the interesting thing is you can do the same thing when n is very big, and then there is more range to tweak this distribution, and actually you can interpolate, if you want, between the uniform spanning tree and independent Born percolation, which is also a determinantal point process, and in between you have a lot of random subgraphs. Okay, another example, slightly more complicated, is taking not H equals to the identity, but H tends to the identity, which is not the same thing because there's actually a discontinuity somewhere. So what we do is that we take a connection which is of the form exponential TA, where A is now just a 2x2 matrix valued one form, which are anti-Hermitian, and we take in the limit t turn to 0. Then it turns out that this couple of graph x1 and x2, they will support on pairs of connected spanning subgraphs such that the total number of cycles in both is 2. So it's quite simple. It could be 2 unicycles, or it could be a spanning tree and a connected guy with 2 cycles, and vice versa. So we understand what are the configuration, and now what are the weights? The weights are actually easy to compute. You have this matrix valued one form. Given a cycle, you can add the form along the cycle. And I take gamma 1, gamma 2 to be basis of the cycles, and then the index I1 just corresponds to, is gamma 1 inside x1 or inside x2? Because as I said, it's just the total number of cycles is 2, but they could be in both x1, both in x2, or separated. And I1 would then be 1 or 2. And then what this means is just I take the first column or the second column. And what I compute then is this determinant, take the square, normalize. And this defines a probability measure, which is again determinantal, and the associated linear subspace H is the image of D plus the vector space generated by the columns of this matrix. Let me just state now the last theorem for this talk. When I have these two graphs, I can define a number above each edge, which is the total occupation number. For example, that edge would have occupation number 2 because on the 2 layers there is an edge. The one below would have occupation number 0, And then a guy which is here, not here, but here would have occupation 1. So this gives me, this is what I call here the trace. It's a random field of numbers in 0, 1, 2, which just gives you the total occupation number. And if you just look at this trace, it turns out that of the previous determinant measure, it turns out that this can be written as you can find two forests of unicycles, so which are graphs with a very specific topology, such that when you put them one on top of the other, they have the same trace. So in rank 1, recall that this was exactly the support of this measure. It's just one unicycle. And in loop, you get a matrix which corresponds to an isomorphism of the fiber at this point. It's an element of SU2. In that specific case, there's a little bit of magic which happens, which is that if you look at the trace, so I recall this is the total occupation number of the x1, x2, its distribution can be factored as the sum of two IID copies of random forest of unicycles, same forest which appear in this theorem, except here they're independent, and their law is determinantal sum to A, except it's quaternion determinantal, which is a special case of the very special case of the Pfaffian case, which was mentioned by Buffetov the other day. And I guess I will conclude on this thing. Thank you very much.
Thank you, Jan. Questions? Okay.
Yes, thank you. I have a question about the DPP matching the edges in the forest of unicycles in the DPP of Kenyan that you mentioned.
Yes?
So, do you know anything about, let's say, if you fix the cycles to which the connected components are routed,
Mm-hmm.
are those cycles also somehow a DPP, or repelling each other like a DPP?
So you in another space, right?
In another space. For instance, for planar graph.
So I had already thought about this question somehow, but I don't have an answer, so I don't know. The only thing I can say is that if you look at this measure in a special case, which is, okay. I mean, the only fact I know which is in favor of this, if you look, for example, at the symmetric case, you have a graph on a cylinder, and you look at the case where your cycles are just winding around like this. You can enforce this. There's a determinant measure on this forest. And if you compute the law of the number of cycles, this is a sum of some Bernoulli with some parameters, which is also what you would get if you would look at the number of points in a determinantal point process. By the way, this number is not fixed, so it wouldn't be a projection DPP. So this is the only thing I can say. I don't know. It would, of course, you would have to go in a space which is a basis of which is given by the cycles of the graph. But the cycles are not really linearly independent because all cycles are allowed. So I'm not sure. I mean, it might be possible, but I don't know.
So this is in the limit of holonomy going to 1. What you showed on the cylinder, it's a measure we obtained with holonomy going to 1.
No, this is just no, you just take a holonomy which is, for example, which is, that's the classical way to do it. You just take a holonomy which is supported, say, on the zipper like this, and then any cycle which would be contractible would have a weight 1, so it wouldn't appear, and a cycle which winds around would get a weight 2 minus z, 1 over z.
Questions?
Yeah, I was wondering whether there exists some nice or natural scaling limits of these DPPs that you Right, I mean, is
Oh.
that the equivalent of a kind of a sine kernel, I mean, on this...
Okay, so I'll give the first answer which came to mind, because there are results, so which I didn't talk about at all about scaling limits, but of course, so famously this model has been shown in the first work by Oded Schramm, who invented the Schramm-Loeffner evolution. It has been shown that if you look, for example, at you fix a point in the middle and you look at the unique path joining this point in the middle at this point here, you take a scaling limit, this converges to what is called SLE2. And if you look also at the curve winding around this random maze, you will get what is called SLE8. So this was the famous work of Schramm and Lorlo Schramm-Werner. And then there are also ways to construct scaling limits in that sense for forests of unicycles, and hopefully maybe also for these other graphs I have shown. But more in the spirit of your question, I think, so the sine kernel, for example, that's a one-dimensional thing. I'm not completely sure, but I think there is work of Titus Lupu, who looks at, the way he approaches the scaling limit thing is to look at graphs which are called metric graphs, where basically you keep some kinds of discrete nodes, but you think of the edges as being continuous segments. And so Lupu has some work where he looks basically at uniform spanning trees, but in this sort of semi-continuous limit on the real line. And he looks at, he has several sort of tree components, and he shows something about, so in some sense, some kind of uniform spanning tree converges to some DPP on R, I think. And I forgot what this law is and if it's related to, I actually don't know, but maybe there's something in that kind of, but it's, I think this is well suited for spanning trees where you just have several connected components. If I'm interested really in this topology with cycles, I don't think on the one-dimensional case it will be easy to see something. It's more two-dimensional, but yes.
Yeah, but still in 2D you could also study some kind of, I mean, what happens when your graph, I mean...
Oh yes, exactly. So yeah, sure. Actually, recently I have talked to, I have been thinking with Wei Xian about this thing which is pictures in black showing it converges to some random fractal. Yes.
I have one actually. So what are matrices? What do matrices help you actually do? Do they help you just represent things mentally and create new DPPs, or were they actually key to approach somewhere?
No. So I mean, yes and no. So the how to say? So there are two answers. Well, first of all, I mean, independently of me, I'm just doing my little thing. I mean, matrices are important. I mean, they are like.
Sure.
There's a huge book by Oxley. It's interesting.
Yeah.
In this context, for us, I mean, it did help us because we're trying. Okay, in some sense, first, why be interested? For example, we saw, like, actually, okay, to tell you the little story how things happen in some sense. We observed these complicated pictures. How to make sense of this? I don't know. I cannot tell you very simply, oh, but the subgraphs you will see, they are just those with this condition and that. So the first case I showed you, which is just on graphs in rank 1, what I have pictured, for example, in this slide, where I knew actually some families with very prescribed conditions, which I know because of baby theory of matrices, just because I'm taking unions and duals, that these are bases of matrices. So therefore, it's almost equivalent to the fact that there are interesting determinantal measures on them. And then we want to find them.
Yes.
These two examples, the connected subgraphs and the spanning forests, okay, we could have found them very differently. But then, these examples,
Yes.
And actually, this example, I still don't know. I cannot give you an explicit formula for a measure on this particular thing. But I know in some sense that if I look at all the graphs which satisfies these conditions, they will have in total 3 cycles and this number of connected components. But also they could have 5 connected components and only 2 cycles. All the one in purple, there's an interesting determinantal measures on these. So it's just, I don't know, it. Yes, I mean, to answer your question, it's not like we used the theorem on page 352 of Oxley about matrices on non-representable fields, and it, no. It's more conceptually to think about these things.
All right.
Also, in some sense, it helps to not really helps, but I mean, in some sense, you know, the fact that the uniform, I mean, that the determinant measure on spanning trees, for example, is uniform. I mean, you can accept that fact, or you can think about it and think it's very weird. I mean, why is it uniform? And this is related to these totally unimodular matrices, which is, you know, subclass of matrices which are very special. So I don't know. It helps to think about these things and organize somehow what we see in families of matrices with certain bases and.
Great. If no more questions, then let's thank the speaker again.